In 13.9, which is the last section for chapter 13, we're going to use vectors to describe the behavior of our graphs in two-dimensional space and in three-dimensional space. The first thing that we're going to talk about is how our graphs curve. To measure curvature, and this is the notation is going to be the Greek letter kappa. So to measure curvature, we're going to use our unit tangent vector. So recall that's the derivative of r over its magnitude. In the definition for curvature, it's with respect to arc length. So remember that this s is arc length. Something to note here, that when we compute curvature, it's not a vector, it's a measurement. So it's going to be a real number or it's going to be a real valued function, but it's not a vector. Now, using a formula with arc length can sometimes be difficult. So we're actually going to use a formula that uses any parameter t. So first recall that our unit tangent vector, capital T, is the derivative of r over its magnitude, or the velocity vector over its magnitude. So when we talk about curvature, it just measures the direction and the steepness of a curve. So in this first diagram, we're illustrating large curvature. If we look at some change in the arc length, and we compare the starting tangent vector to the ending tangent vector, if there's a large change in the direction of these tangent vectors, which in this diagram there is, they're clearly going in very different directions, then that would correspond to a large curvature. And just looking at this curve, you see that it does curve quite a bit. To look at an example of small curvature, we're going to look at this second diagram. So we have this same change in arc length, but in this diagram, look at our starting tangent vector and our ending tangent vector. The change in direction of those vectors is very small, so that would correspond to a small curvature, and if you look at this curve, clearly it doesn't curve very much. So using a formula with arc length can sometimes be difficult. So instead we're going to use this curvature formula. This says to compute curvature, you can take 1 over the magnitude of the velocity times the magnitude of the derivative of the tangent vector with respect to t, or in other words, the magnitude of the derivative of the tangent vector over the magnitude of the derivative of r. And really those formulas say the exact same thing. In example 1, we're trying to find the curvature for a line, r of t equal to 2t negative t, 5 plus t. Notice that this is a line. So if I were to compute the curvature, I would think that it would be 0 because lines don't curve. So let's verify that by first computing our unit tangent vector, which is the derivative of r, and that would be 2, negative 1, 1. And we'll divide by the magnitude of the derivative of r, which would be the square root of 4 plus 1 plus 1. So we have 1 over the square root of 6 times this vector, and I'm not going to bother to distribute. I'll just leave it that way. So the next thing I want to do is I want to compute the derivative of my unit tangent vector. So the derivative is going to be 1 over the square root of 6 stays, that's the constant. The derivative of 2, negative 1, 1 is the 0 vector, 0, 0, 0. So if I were to take the magnitude, that's simply 0. So if the magnitude of the derivative of the unit tangent vector is 0, then when I look at this fraction with the numerator of 0 and the denominator is not 0, then I could see that the curvature here with respect to our parameter t is 0. And that makes sense because r was a line, so the curvature should be 0. So let's move on to another example. Let's say that we wanted to find the curvature for this circle, 3 cosine, 3 sine. Now this is a circle, so I'm thinking the curvature can't be 0. And the first thing I would like to do is compute my tangent vector and my tangent vector. So my tangent vector would be the derivative of r over its magnitude. So the tangent vector is going to be equal to the derivative of r is going to be the vector negative 3 sine of t, 3 cosine of t, and then divide by its magnitude. And the magnitude is going to be 3 when I compute it, because it'll be 9 sine squared plus 9 cosine squared, which is simply 9, and then you take the square root and you get 3. I'm going to go ahead and simplify this because I can divide by 3 to get the vector negative sine positive cosine. Computing the derivative, that's going to be equal to the vector negative cosine, negative sine. Sorry, my pen's not working. So when I compute the magnitude, it's going to be 1, because I'll get the square root of cosine squared plus sine squared. My curvature is going to be equal to the magnitude of the derivative of the unit tangent vector over the magnitude of the derivative of r. And the magnitude of the derivative of our unit tangent vector is 1. So the magnitude of the derivative of r, well, the derivative of r is our negative 3 sine t, 3 cosine t. That was in the numerator when we computed our tangent vector. Its magnitude is simply 3. And that makes sense. Okay. So something interesting is when we look at our curve, notice that the radius is 3. So you're free to use this. That when you're computing curvature, all circles have a constant curvature of 1 over the radius, which is what we got when we computed our curvature. We got 1 over the radius 3. There are alternative formulas. If you look into this next box, you see that we can also compute our curvature by looking at the magnitude of the cross product of the velocity with the acceleration vector over the magnitude of the velocity vector cubed. Okay, so just recall that our velocity vector is the derivative of r, and our acceleration vector is the derivative of our velocity vector. Well, let's go ahead and use this formula to compute the curvature of this helix. And this will probably take a lot of space. And we're going to use this alternate formula. So the first thing I need to do is to figure out what my velocity vector is. I have r, the velocity vector is just the derivative of r. So my velocity vector is going to be negative sine of t cosine of t, comma 3. And my acceleration vector is simply the derivative of my velocity vector, which would be negative cosine, negative sine, 0. So let's go ahead and compute the cross product of V cross A. Now remember, when we do cross products, the direction matters. So my I, my J, my K. For my first vector V, that will be negative sine t, j is cosine of t, and k is 3. A is negative cosine of t, j is negative sine t, and k is 0. Computing, so remember the I component, I cover the I, and I have cosine 3, negative sine 0. So it's going to be 0 minus negative 3 sine of t, which gives me a positive 3 sine ti, minus my j, covering j, is going to be 0 minus a negative 3 cosine of t, which turns into a minus 3 cosine t j. And then covering the k, I have sine squared t minus a negative, so plus cosine squared t. That's just 1, so it's going to be plus k. So now I need the magnitude of this cross product, which would be the magnitude of this vector. Let's see if I can make this long enough. So square the first term, I have 9 sine squared t plus square the 3 cosine to get 9 cosine of t, cosine squared of t, sorry, and then plus 1. So 9 squared t plus 9 cosine squared t is just going to be 9, plus 1 gives me the square root of 10. The next thing I want to compute is the magnitude of the velocity vector, and then I'm going to cube that. our velocity vector, magnitude, and then I'm going to cube, would be sine squared t plus cosine squared t plus 9. So that would be the square root of 10 cubed. Putting this all together, my curvature will be the square root of 10 over the square root of 10 cubed. So when we simplify this or reduce this, it's simply 1 over 10. And that would be the curvature of this helix. So remember the helix, and this is in three-dimensional space. So in this case, it's circular. It looks like a spring, right? So it makes sense that it has curvature. As with a circle, helix is similar to a circle, except for it's like a spring. It just keeps going up or down. So if you do have a helix, and you're free to use this, of the form a times cosine of t, a times sine of t, so circular, not elliptical, and then the last term, b times some value of t. If your helix looks like this, then your tangent vector will be negative a sine t, a cosine t. I've got to change my pen, comma b, divided by the square root of a squared plus b squared. And your curvature will simply be a over this over a squared plus b squared. If we look at our example that we had, our a value was 1. So we're looking at our original equation r. So here the a value is equal to 1 and the b value is equal to 3. So just to verify, we would have 1 over 1 plus 9, which is 1 over 10, and that's what we got. I'm going to pause, and I'm going to change the tip of my pen and see if it helps. Okay, so we used our tangent vector to measure the curve, or to find the curvature. The next concept we're going to talk about is our principal unit normal vector. So our principal unit normal vector is a vector that's normal to our unit tangent vector. To compute the principal unit normal vector, and oftentimes I'll just say unit normal vector or normal vector. With respect to arc length, it would be the derivative of the tangent vector over its magnitude. Or another way to look at it is to take the derivative of our tangent vector and then multiply it by 1 over the curvature. So again, oftentimes using arc length is difficult, so instead we'll just use any parameter t, and the formula is the same, derivative of tangent vector over its magnitude. Let's look at this diagram here. So first of all, we have this curve, and notice the direction that this curve is generated in is kind of left to right. So at any point on this curve, the tangent vector is going to be going in the same direction that the curve is generated in, and it's measuring curvature. So the normal vector is perpendicular or orthogonal to our tangent vector at any point. And something to note is that the normal vector is pointing in the direction of the curve. Okay, so in the direction that the curve is turning. And that would be in these properties in this box. Okay. Tangent normal vectors are orthogonal. So what that means is that when you take their dot product, it's 0. This normal vector points to the inside of the curve, so it's in the direction that the curve is turning. Let's go ahead and find our principal unit normal vector for this helix in example 4. So the first thing I'm going to do is I'm going to compute the tangent vector, and that would be the vector -5 sine, 5 cosine, 7. And then over the magnitude, would be the square root of 25 sine squared plus 25 cosine squared would just be 25 plus the 7 squared, which is 49. So this turns out to be 1 over the square root of 74, and our vector is -5 sine, 5 cosine, 7. So my normal vector is the derivative of this tangent vector. So this normal vector is going to be the derivative of the tangent vector over its magnitude. Derivative of the tangent vector is 1 over the square root of 74, and the derivative of this vector is going to be -5 cosine of t, -5 sine t, 0, over the magnitude here. So the magnitude is the 1 over the square root of 74 times the magnitude of this vector, which is the square root of 25 or 5. Notice that the 1 over the square root of 74, that's going to go ahead and cancel. And my normal vector is going to be -5 cosine, -5 sine, comma 0, but I'm dividing by 5. So it's going to be negative cosine of t, -sine t, 0. All right. So something to note is if you do have a helix of this form, and you're free to use this, this will always be its principal unit normal vector. Okay, negative cosine, -sine, comma 0. So now if I were, although this is not part of the example, it's not part of the question, if I were to check to make sure that I got the right normal vector, all I have to do is dot product the tangent vector with the normal vector and see if I get 0. So my tangent vector, 1 over the square root of 74. The vector was negative 5 sine t, 5 cosine t, comma 7. And I'm going to dot that with my normal vector, negative cosine of t, negative sine t, 0. So if these guys are orthogonal, this dot product should be 0. I'm going to ignore this 1 over the square root of 74. When I dot these two vectors, it's going to be negative 5 sine times negative cosine. So it's going to be a positive 5 sine of t cosine of t. So multiply, add, multiply, add. So the 5 cosine times negative sine would be a negative 5 sine cosine. So this becomes a minus 5 sine cosine. And then plus 0. Oops, almost made a vector notation. Okay. So this is simply 1 over the square root of 74 times 0, which is 0. So it checks out. These guys are orthogonal to each other. So their dot product is 0. The next thing we're going to talk about is we're going to talk about our acceleration vector. And one thing we can do with our acceleration vector is we can break it down into the addition of our tangent and our normal vector. So we're going to have a tangential and normal components of our acceleration. So the acceleration vector can be any magnitude or any length. So when we break it down into the addition of the normal and the tangent vectors, we're going to have this coefficient a sub n on our normal vector and a sub t on our tangent vector that we're going to have to compute. So the reason why we want to break down our acceleration vector is typically if you want to change your object, change maybe the speed or its direction, you change the velocity, okay? And when we change the speed, what we're doing is actually we're looking at acceleration in the direction of our unit tangent vector. And then when we change direction, we're changing the acceleration in the direction of our unit normal vector. Okay? So oftentimes it's nice to have the acceleration vector broken down in pieces so we could see how the speed and the direction is changing. So there is a formula, as always. It may not be easy to use. So the goal is to find your normal tangent vectors, but also this a sub n, a sub t that would be the coefficient on those vectors. So to compute your a sub n, it's actually the curvature times the magnitude of the velocity squared. And that's not so bad. Okay? Or magnitude of velocity cross acceleration over magnitude of velocity. So again, that's not so bad. The problem is computing the a sub t, the coefficient on the unit tangent vector. It's actually the second derivative of arc length with respect to t. That's difficult to compute. So instead of that, we can go back to our projection vectors in the very beginning of this chapter, and we can use the scalar component of the projection vector, and that just turns out to be the coefficients. So the alternate form that you should use, and it's not specific in your textbook, is that to compute a sub n, you're going to take the dot of the acceleration with the normal vector. To compute a sub t, you're going to dot your acceleration with the tangent vector. And that's much easier to use. Okay, again, that just comes from the scalar component of projection vectors. It might be easier to see if we look at this diagram here. So again, we have some curve. And at any point, we'll have our tangent vector. And orthogonal to the tangent vector would be our normal vector. So when we think about vector addition, what we can do is we can break down our acceleration vector to be the addition of our tangent and our normal vectors. So you see how the acceleration is between those two. So you can see it as the addition of those two vectors. In example 5, we have this object. It's going to follow this parabolic path, and R describes the parabolic path. We want to find the tangential and normal components of the acceleration of the object. So that would just be the a sub n of n and the a sub t of t. So I'm going to use the alternate formula. I need my velocity vector. So I have r, velocity vector, is going to be 2, 2t, so just the derivative of r. And I'll also need that acceleration vector. So derivative of velocity would give me 0, 2. So I need to dot the acceleration vector with the normal vector and the acceleration vector with the tangent vector. Only I don't have my tangent or my normal vector. So the first thing I'm going to do is compute the tangent vector, which is 2, 2t, over magnitude. The magnitude is going to be the square root of 4 plus 4t squared. So it's okay to have a variable magnitude. Now if I factor out a 4, that would be the square root of 4, or 2, and divide by 2, I can write this in a simpler form as 1, t over the square root of 1 plus t squared. So I have this tangent vector, and I can now figure out what my a sub t is. So my a sub t, the coefficient on the unit tangent vector, is going to be equal to the dot product of these two vectors. So it might be easier to dot them if I write my tangent vector as a single vector, 1 over the square root of 1 plus t squared, t over the square root of 1 plus t squared. And dotting these two, I end up with 2t, so remember, not a vector, it's a dot product, over 1 plus t squared, or the square root of 1 plus t squared. So I got my a sub t, which means my a sub t of the tangent vector, so this would be the tangential component. Multiplying that, I get 2t over 1 plus t squared, 2t squared over 1 plus t squared. Again, I'm just taking my a sub t and I'm multiplying it by my tangent vector. So this would be the tangential, oops, I forgot to close my vector, sorry. This is my tangential component. Now I'm going to figure out the normal component. Well, I have my acceleration vector. All I need is my normal vector. So my normal vector, recall that that's going to be the derivative of the tangent vector over its magnitude. And I have my tangent vector, so if I were to compute the derivative of the tangent vector, oh, and this is written in terms of square roots. I'm going to go back up to my tangent vector and write this as 1 over the square root of 1 plus t squared would be the vector in parentheses 1 plus t squared to the negative 1/2. And then the other component would be t times 1 plus t squared to the negative 1/2. It may be easier for me to compute the derivative of the tangent vector if I wrote the tangent vector that way. Because the first component would be negative 1/2, inside stays the same, to the negative 3/2 times the inside, which would be 2t. So negative 1/2, inside stays the same, negative 3/2 times 2t. And it looks like I can simplify that a little bit. But let's go to the other component. I have to use both product and chain rule. So derivative of t is just 1. The 1 plus t squared to the negative 1/2 stays the same. Plus the t stays the same. The derivative would be negative 1/2 times 1 plus t squared to the negative 3/2 times 2t. Well, that's ugly. Let me go ahead and simplify this. Let's see, first component, I got some 2's canceling. It looks like it's going to be a negative t over 1 plus t squared to the positive 3/2 if I make it a positive exponent, comma. On this other one, 2's cancel. I have t squared. If I do some algebra and simplify, it looks like it'll simplify to 1 over 1 plus t squared to the 3/2. So double check me on that, because in my head I was just combining those like terms, adding them up. Remember, that's just the derivative of our unit tangent vector. I still, to find my normal vector, need to take this vector and divide by its magnitude. I have to take this vector and I never make my lines long enough. Divide by magnitude. All right. Oh, the magnitude here would be the square root of, it becomes t squared over, if I square the denominator, I get 1 plus t squared to the 3rd power, and this will all be under a square root. 1 over 1 plus t squared. to the third power, all under this square root. Whee. Let's see. So numerator stays the same. The denominator is going to be t squared plus 1 over 1 plus t to the third. Can cancel to get 1 over 1 plus t squared squared, and then square root. I'm doing a lot of this in my head. So again, the numerator is going to stay the same. But the denominator simply turns into 1 over 1 plus t squared. And that's it, right? The square root cancels. Let's see. So if I were to multiply my vector by the reciprocal of our denominator, I get this vector negative t over the square root of 1 plus t squared. Next component is 1 over the square root of 1 plus t squared. And that's just my n. Remember, I still have to put all this together. So my a sub n is going to be equal to the vector a dotted with the vector n. My vector a was 0, 2, so I'm going to dot it with this vector n. And let's see what we get. Okay, so 0, and then I'm going to add 2 times. Simple. That's just going to be 2 over the square root of 1 plus t squared. Some of these problems are very, very long. All right, so I got my a sub n. Now my normal component, a sub n times our normal vector, is going to be the vector negative 2t over 1 plus t squared, comma 2 over 1 plus t squared. Whew, that was long. So we found the components of our acceleration vector. The last topic in this section that we need to talk about is movement in three-dimensional space. So far, when we're talking about our tangent and our normal vector describing the curvature, we're looking at movement in two-dimensional space. Think about the tangent and the normal vectors. Think about the plane that passes through them. So I'll just call that the tangent normal vector, or the TN plane. Okay? We want to move in 3 dimension, so we need another vector to describe this third dimension. And that's going to be our binormal vector. Okay? We're going to use a capital B for a unit binormal vector. So we have a unit tangent vector because it's length 1, a unit principal normal vector because it's length 1, and now we have a unit binormal vector because it's length 1. And we find this binormal vector by just taking the cross of the tangent with the normal vector. And remember, order matters. So here's our definition for the unit binormal vector. And what goes with the binormal vector is what we call torsion. Torsion and curvature are similar. So curvature is the way the graph turns, and we use our tangent vector to describe that. But when we come out of that two-dimensional plane of tangent normal vector, torsion is that curvature or that twisting in our third direction. Okay? So to compute the binormal vector, that's fairly easy. You just cross the tangent and the normal vector. But to compute torsion, and remember, torsion is similar to curvature in that it's not a vector, it's a measurement. Okay? So to compute torsion, it's going to be the negative derivative binormal vector with respect to arc length dotted with your normal vector. Again, that's going to be a very difficult formula to use. Okay? And also remember that torsion, not a vector. Similar to curvature, it's just a measurement. So we do have some alternate formulas. The binormal vector, not an issue, but you can also look at it as a cross between velocity and acceleration over its magnitude. Torsion, on the other hand, and we use this Greek letter tau for torsion. If you don't want to use arc length, you can always use that it's the cross product of the velocity with the acceleration dotted with the derivative of the acceleration over the cross product, the magnitude of the cross product squared. And then you can also write this in terms of r, because the velocity is the first derivative of r, acceleration is second derivative of r, and so on. So you get the same formula. So you're also free to use that formula there. Now, this diagram kind of describes what I was talking about, where your torsion, which you need your binormal vector for that, is sort of this twisting out of the plane determined by the tangent and the normal vectors. So we have movement in our plane determined by the normal and the tangent vector. So we're describing movement here, but objects don't just move in two-dimensional space. They also come out of that plane, and that's where your binormal vector and torsion comes from. Okay, so that's the basic idea. Let's go ahead in this last example. Oh, just one more thing. I'm not sure if you'll see this in your physics class, but oftentimes they will describe this as the TNB frame. So it's describing movement using tangent, normal, and binormal vectors. This will be our last example for this section. And we're going to compute the torsion of this helix. So to compute the torsion, I'm going to first find our tangent vector. And this would be negative sine t cosine of t, comma 1. Divided by magnitude, so sine squared plus cosine squared would be 1 plus 1. Or 1 over the square root of 2 times the vector negative sine cosine 1. Okay. So first note that since this is a helix of that form, a cosine, a sine, bt, we have a equal to 1 and b equal to 1. I don't actually have to compute the normal vector, I know from the previous example, and this is where you get to use this, the normal vector is negative cosine t, negative sine t, comma 0. So to compute the binormal vector, or unit binormal vector, I need to cross that unit tangent vector with the unit normal vector. Notice that my tangent vector has the 1/2 on the outside of the vector. So I'm allowed to take that 1/2, 1 over the square root of 2, figure out what the cross is, and then multiply by the 1 over the square root of 2. So that's just one of the properties we had when we were talking about vectors. So again, we have our I, our J, our K. And our tangent vector, we have negative sine, cosine 1. And our normal vector would be negative cosine, negative sine 0. When I cross, remember I still have the 1 over the square root of 2. I'm going to leave it in vector form. It's easy for me to see that this is going to be covering the I. It's 0 minus a negative sign, so it becomes sine. Covering the J, I have 0 minus cosine, so that's negative cosine. And then covering the K, I have sine squared plus cosine squared is 1. So I have my binormal vector. To figure out torsion, I can look at that as the negative of the binormal vector over the magnitude of the velocity dotted with the normal vector. I could use that formula. I don't really have the magnitude of the velocity, so I could simply figure this out. My velocity vector is negative sine cosine 1. So the velocity here is going to be the square root of sine squared plus cosine squared plus 1, or the square root of 2. And I already have my binormal vector, so I need its derivative. Oops, sorry, I'm supposed to have a derivative here. So there's a lot of formulas you can use. We have a lot of alternate formulas. So I'm just using this formula. The torsion is the negative of the derivative of the binormal vector over the magnitude of the velocity. And then the derivative would be 1 over the square root of 2 times the vector cosine sine 0. So putting this all together, negative derivative of b over the magnitude of v dotted with the normal vector will be negative 1 over the square root of 2 times the vector cosine sine 0 divided by magnitude of our velocity was square root of 2 dotted with our normal vector, which was negative cosine negative sine 0. This will be equal to negative 1/2. So that's a negative 1 square root of 2 divided by square root of 2. And then the dot product of these two vectors would be negative cosine squared minus sine squared. And then plus 0. Factoring out a negative, cosine squared plus sine squared is 1, and I will get a positive 1/2. So this is going to be our torsion. All right, so that's going to be it for this section.